Hello. In this video, I'm going to be solving exercise 1.3.12 from Jiří Lebel's notes on Diffy Qs. So suppose a cup of coffee is at 100 degrees Celsius at time t equals 0, it is at 70 degrees at time t equals 10 minutes, and it is at 50 degrees at time t equals 20 minutes. Our task is to compute the ambient temperature. So this is going to be another Newton's law of cooling problem, as we can see, but this one's slightly different in flavor. So usually, at least with the Newton's law of cooling problems I've seen, we're given the ambient temperature and then we're given the temperature at like some measurement or two, and we're asked to determine at what time how long it will take for the cup to reach another specified temperature. Here we're going backwards. So we've taken 3 data points that at t equals 0, and I'll write this down too. So at t equals 0, we have 70 degrees Celsius, t equals 10, we have 50 degrees Celsius, and at time t equals 20, we have, 170 and then 50. And our goal here is to work backwards and instead find the ambient temperature, which I'm going to call A. Okay, so like I mentioned, this is going to be a Newton's law of cooling problem. We're going to assume that the temperature of the cup changes according to Newton's law. So let y of t be the temperature of the coffee, of the cup of coffee, at time t greater than or equal to 0. So Newton's law of cooling states that this is going to be proportional to the difference between the ambient temperature and the temperature of the object the temperature of the object we're interested in. So the change in temperature, rather, dt over dt. And I guess actually, to be consistent, let's actually let this be capital T for the temperature. So by Newton's law of cooling, this is going to be proportional to the difference between the ambient temperature A and, I wrote the y again, and the temperature of the coffee, capital T. In other words, what this proportionality symbol means, what does that mean? There is a constant k such that the derivative of the temperature with respect to time is proportional to A minus the temperature, where k is a constant. Okay, so now we have our model that we're going to use to compute the temperature or the ambient temperature. And the first important note I'm going to make, let me write this down, is this. So notice that the cup started at 100 degrees Celsius at time t equals 0, and it's decreasing. So after 10 minutes, it's gone down to 70 degrees, and after 20 minutes, it's gone down to 50 degrees. So what this tells me is that the ambient temperature has to be lower than the temperature of the cup. And if you just think about how a cup of coffee cools over time, ideally rather, it'll get closer and closer to that ambient temperature without ever actually reaching that ambient temperature. So here we can see that we've gone to 70 and then 50. And so our ambient temperature has to be lower than these numbers. And more generally, A must be smaller than T of t for all times t bigger than or equal to 0. And the reason it holds for all times, again, is because the temperature is going to get closer and closer to A, this temperature here, but it's never going to actually equal A. It's never going to reach A. It's just going to get closer and closer to A. This is going to be important in just a bit, so let's keep this in the back of our mind. And so, okay, let me just clean this up a little bit. All right. In symbols, this is saying that A minus T of t has to be less than or equal to, or actually less than. So you already can assume it's less than. Again, the temperature, capital T, never reaches the ambient temperature. So that's a strict inequality. Okay. So with this out of the way, let's get down to business with solving this differential equation. So we have dt over dt equals k times a minus t. We already see that this is a separable equation. We can see this by just noticing that this term is a function of time, and this term depends on capital T rather, and everything else we could just leave as it is. Or if we're being more transparent, I can divide by a minus t dt over dt, and then just leave the k on the right side. And so here I'm going to stick with the usual way we talk about solving separable equations, which is that trick of like multiplying the differentials. So if we do this, we get dt over a minus t equals k dt. This isn't the most rigorous way to solve these types of equations, but I think it's helpful for an exam because it's easier to memorize, and so that's why I'm going to stick with this method. And so if we integrate, we're going to get this. This is equal to integral of k dt. Okay, so doing some mental integration, the left side is negative ln absolute a minus t, and then the right side's going to be k times t plus some arbitrary constant c. Okay, oops. Sorry about that. I forgot I had not erased the notes from the second page. So where were we? We had negative ln a minus t equals kt plus c. Or we can rewrite this, and let me actually center this over here. Or negative ln, if we just add the variable t right here into our function, this is kt plus c. And you'll see why I did this in just a bit. So this is where, or actually, okay. What we can do at this point is we can solve for the absolute value in here. And when we do this, what we're going to get is that first ln absolute a minus t at t equals c prime minus kt, where here I've just let c prime denote this arbitrary constant negative c. You can just keep it as c if you want. I prefer to add the primes to emphasize that it is strictly a different constant, but it's a personal preference thing. And so then if we take exponentials, a minus t of t, this will be e to the c prime minus kt. And here we can do c double prime e to the negative kt, where now c double prime is the constant e to the c prime. Okay. So now we have this issue of getting rid of the absolute values. And this is exactly where this remark I made, this notes, is going to come into play. So because we know a minus capital T at t is less than 0 for all times t, what this says is that this guy right here, this absolute value, just becomes equal to negative a minus t of t. Again, because the inside is negative. Since a minus t of t is less than 0 for all t bigger than or equal to 0. So our new equation is negative a, or even better, just distributing the negative right here, we get t at t minus a equals c double prime e to the negative kt. And so our temperature function is just a plus c double prime e to the negative kt. All right. So now we have this. And at this stage is where we're going to incorporate the data we were given at the beginning of the problem. Remember that we know that at t equals 0, our temperature is 100, at 10 it's 70, and at 20 it's 50. And so for our function, this means that's 100 equals, this is our temperature at time 0, but this is equal to e to the negative k times 0, which is a plus c double prime. We have that 70 is the temperature at time after 10, at time t equals 10. And this in turn is equal to e to the negative 10k, just plugging in 10. And 50 equals t of our temperature function at 20, sorry. And this in turn is e to the negative 20k, which for purposes you'll see in just a bit, I'm going to rewrite this exponential as e to the negative 10k all squared. Okay, so we thus have the system 100 equals a plus c double prime, 70 equals a plus c double prime e to the negative 10k, and 50 equals a plus c double prime e to the negative 10k all squared. Notice that we can simplify this system a bit by just letting x denote this quantity e to the negative 10k, which occurs in both of our equations. And again, I keep forgetting about those notes. I'm sorry. So I'm going to let x equal e to the negative 10k. Then our system is going to become the following. Oops. Our system becomes 100 equals a plus c double prime. Let me clean that. 70 equals a plus c double prime x. And 50 equals a plus c double prime x squared. So let's call these equations 1, 2, and 3. So now is the tricky bits where we have to solve for this system. Now notice that as soon as we solve for x, or really we solve for a, c double prime, and x, we're done. We don't need to revert back to x and figure out what k is because we don't care about k in this problem. All we care about is what the value of a is, right? So, okay, to this end, well, one thing that we can do is take, okay, so from equations 2 and 3, we have, just notice, or here, I'll write it actually. 70 minus c double prime x equals a, just by subtracting this to the left side. And in equation 3, we have 50 minus c double prime x squared equals a. And so, because the right sides are equal, we must have that 70 minus c double prime x equals 50 minus c double prime x squared. But notice that we can play the same game with 1 and 2. So from 1 and 2, if I subtract this c double prime to the left side, I get 100 minus c double prime equals a. And from equation 2, once again, we'll just recycle the same equation, minus c double prime x equals a. So we can set these a's equal to each other, and we get that 100 minus c double prime equals 70 minus c double prime x. Let me call these 4 and 5. So now our task has become solving 4 and 5 jointly. Now 4 rewrites as follows. So just bringing all of the numbers to one side and then the c double prime x's to the other side, we get that 20 is c double prime x minus c double prime x squared. And this in turn is equal to c double prime x 1 minus x. And we can play a similar game with 5. So this rewrites as, well, now it's 30 minus c, or equals c double prime minus c double prime x, which is c double prime 1 minus x. And what's awesome here is that we have c double prime times 1 minus x occurring in this equation right here. And we know what that value is. So we know that whole thing, c double prime times 1 minus x, is equal to 30 because of this right here. So subbing this into, let's call this equation 6. Subbing this into 6 is going to therefore give us that 20 equals x times 30. And so x has to be 2/3. Nice. If I call this equation 7, then from 7, we get that c double prime equals 30 over 1 minus x, which is 30 over 1 minus 2/3, which is 30 over 1/3, and this is 90. So now we know c double prime. And once we know c double prime, we can go back up to 1 and figure out what a is. From 1, just solving for a, we get that a is 100 minus c double prime. And, well, c double prime is 90, so this tells us that a has to equal 10. And that's our final answer. The ambient temperature evidently is 10 degrees, and don't forget your units, Celsius. Okay, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.